All right, so now we have biconditional statements. So given the conditional statement, determine if it's true, then write it as a converse and determine if that is true. If both are true, then write it as a biconditional statement. So an angle is right, then its measure is 90 degrees. So since it's true this way, or reading it this way, it's true. Now we're going to read it backwards, or we're even going to write it backwards, i.e. the converse. If an angle measure is 90 degrees, then it is right. And that's true. All right. And then this is going to kind of play in with logically equivalent. But when the conditional statement is true, the converse is true, all forms are true. And when all forms are true, we can write it as the mighty biconditional statement. And in my opinion, the biconditional statement is the easiest to identify. Why? Because look what I'm writing right now. An angle is right if and only if it is 90 degrees. All right. Notice how I have this if and only if smack dab in the middle. That's the giveaway. I can even write an angle is 90 degrees if and only if it is right. So the order doesn't even matter when you write a biconditional statement because it's true either way. All right, next I have if two angles are adjacent and supplementary, then they form a linear pair. True. They're adjacent, they're supplementary, they form a linear pair. Now let's write it as its converse. So let's swap the order, go the different direction. If two angles form a linear pair, then they are adjacent and supplementary. I'm just going to kind of shorthand it, running out of room, adjacent / sup. And that is true. All right, linear pairs are adjacent and supplementary. So again, since both directions are true, I can write it as the mighty biconditional statement. Two angles form a linear pair if and only if and only if they are adjacent and supplementary. Alright, so that's the biconditional. It's true in both directions. So when you're checking the truth of a biconditional, you need to read it in both directions. And then logically equivalent stuff, something we already mentioned again, just be a little bit more formal about it. Conditional / contrapositive are either both true or both false. Barely cram that in there. All right, they're either both true or both false. And then that's same for converse and inverse. The converse and inverse are the same. They're either both true or both false. Whew. All right, a lot going on. Properties and stuff. All right, so let's review some properties. Going to be writing these from scratch, but we have the reflexive property. And we're just going to stick in the algebraic world right now, but this works for segments and angles for any A that is a real number. So think of any real number that you can think of. 7. All right, basically it's saying 7 equals 7. So a number is equal to itself. Isn't that crazy? Mind blown. All right, hopefully your head doesn't hurt from all this difficult content we're talking about. All right, when does this come useful? This comes useful in Unit 4. We use reflexive property a lot. Next we have symmetric. All right, if A equals B, then B equals A. So, reminder, I like to say symmetric, you swap the order. Reflexive, you like to repeat what you have. All right, these two are incredibly easy to understand, yet students like to confuse them all the time. All right, don't confuse which one's which. Next, I got transitive. So basically it's saying if two things equal the same thing. So like if A equals B and A equals C. Well, A equals B, A equals C. So since they equal the same thing, they equal each other. All right, when two things equal the same thing, they must equal each other. And then next we got substitution. Substitution's an easy word to misspell. Sometimes you just don't know how many T's are in there. Like in the past, I've spelled substitution like this. You just kind of get confused and lose track of where you're at. Next thing you know, you got like 7 T's in there. But anyways, if A equals B and then A plus C equals D, I'm allowed to replace A with B. I'm allowed to substitute it in. See how it's named substitution? And I like to think about basketball where you replace one player, you just sub one guy out. All right, and that's substitution. All right, and then remember, we started 2-column proofs with algebra. Why? You guys had a whole class on algebra. So basically it's, let's learn something new, 2-column proofs, but we're going to start with something you guys are familiar with. All right, so I have my statements, I have my reasons. The construction of a 2-column proof is what you're given is always going to go first. So in this case, 2 parentheses 3x minus 2 equals 26 and given. Remember, my first statement is always given. If you can understand how proofs are constructed, you might stink at proofs, but if you know the most basic of patterns, you always get the first statement and reason. All right, from here, it's just about to start some calculations. So I'm distributing the 2 inside the parentheses. So I'm going to get 6x minus 2. Excuse me, I almost had a brain fart. 6x minus 4 equals 26. And all I did was distribute. You might write distributive property of equality, or equality, whatever you want. I like to keep it simple and just write distribute. Now it's like, what am I going to do with this minus 4 right here? Well, I'm going to get rid of it by adding 4 to both sides. How do you undo subtraction? Addition. All right. So I'm literally solving an equation, and I'm explaining my thought process as I go. Same with this 6. How do I undo the 6 times x? Well, I'm just going to divide both sides by 6, and I get division. All right. And then I know I'm done, because remember, you always want to end at what you're trying to prove. X equals 5, x equals 5, I'm done, smiley face. All right, and in future videos, we're going to be doing segment and algebra proofs.